the tips of our noses to the farthest flung galaxies. This analogy captures the magnificence of LIGO. It's about much more than proving a scientific prediction. LIGO enables us to perceive the physical universe and understand reality on a new level. Like photons, gravitational waves travel at the speed of light as they ripple across space-time. Their signals are all around us. By listening for gravitational waves with some of the most sensitive instruments ever built, scientists are recording tremors of distant violent events. The formation of black holes, supernova explosions, and potentially exotic phenomena we haven't discovered yet. So what are gravitational waves? What causes them? And why is LIGO's ability to detect them already transforming our understanding of the universe? I'm Alex McCohen, and you're watching Astrum. Join me today as we learn about gravitational waves, unpack the groundbreaking technology behind LIGO, and anticipate some of the stunning developments that lie around the corner. Gravitational waves are one of the stranger implications of Albert Einstein's general theory of relativity. As we've covered previously, space-time is a model that combines the three dimensions of space and the fourth dimension of time into a single manifold. All objects with mass create curvature in space-time, and objects with a lot of mass create a lot of curvature, which we experience as gravity. A simple way to visualize this is to think of a pool ball resting on an elastic surface and a bowling ball resting on that same surface. The more massive bowling ball will create more curvature. As objects move across space-time, that curvature changes position with them. One of the amazing consequences is that when objects of a certain mass accelerate, they can send ripples across space-time as gravitational energy. While this requires a special set of conditions, namely, a very massive object undergoing acceleration, such a cataclysmic event would send ripples or gravitational waves outward at the speed of light. Think of them like ripples on a pond, but instead of water, they travel through the fabric of space-time in all directions. As in the pond analogy, these disturbances become weaker as they radiate outward. To an observer, the distance between objects would appear to expand and shrink as the gravitational wave passes. Mind-boggling to imagine. Yet, although Einstein predicted the existence of gravitational waves, he was pessimistic about our chances of ever detecting them. He thought that these disturbances would be so small as to escape our ability to measure them. And who could blame him? Many of the changes in distance that LIGO seeks to measure are 1/10,000th the length of a proton. Yes, you heard that correctly. 10,000 times smaller than a single proton. And yet these signals would come encoded with all kinds of information about their origins, when they originated, how far they traveled, and what kind of event produced them. This is where LIGO comes in. It consists of two observatories funded by the United States National Science Foundation and operated by MIT and Caltech. Among its driving forces are renowned physicists Kip Thorne, Raina Weiss, and Barry Barish, all of whom shared the 2017 Nobel Prize for their decisive contributions to the detection of gravitational waves. LIGO is essentially a large-scale and very sensitive interferometer, an invention that's been around since the 1880s. An interferometer essentially measures what happens when light waves are combined from two or more sources. For example, you could use an interferometer to test whether light travels at different speeds through different substances, such as through air or water. Even a subtle difference in speed will produce an interference pattern when the light waves combine, much like what happens when two ripples on a pond intersect. If the peak of one ripple hits the value of a second ripple, they will subtract from each other, producing a flat surface. However, if the peaks line up exactly, it means the waves are in phase and add to each other. This is essentially what the interferometer measures with light. By seeing how in or out of phase two light waves are, an observer can infer the relative speed of the waves. And the larger and more powerful the interferometer, the more sensitive it is. Here's how it works. LIGO has 2 observatories located in Hanford, Washington, and Livingston, Louisiana. Why 2? Well, you need at least 2 detection sites to triangulate where the signals are coming from. Each observatory continuously fires a powerful laser at a beam splitter positioned at a 45.8 degrees angle. The laser beam has to operate at around 750 kDq, powerful enough to vaporize you completely if you got in its path. The splitter then splits the laser beam perpendicularly. The light in each arm travels down a 4-kilometer vacuum cavity with a mirror at the end of it. The beams then bounce between this mirror and a recycling mirror at the other end nearly 300 times, increasing the distance from 4 to 1,200 kilometers. Remember what we said with interferometers. Bigger is better. After completing nearly 300 trips, the laser beams combine at the beam splitter and head to a photodiode, which is a light-sensitive semiconductor. If undisturbed, the beams will be in phase, meaning their frequencies will subtract each other and 000709. No light will arrive at the photodiode. But if there's a gravitational wave, the distance each beam travels will be slightly different and they'll be out of phase. The photodiode will pick up a signal indicating the presence of a gravitational wave. Now this is how it works in a perfect world. But in reality, the interferometer is constantly picking up noise. To minimize this, LIGO uses incredibly smooth 40-kilometer mirrors suspended by silica threads. Any particles in the interferometer's arms are also a problem, which is why LIGO pumps the air from its vacuum chambers to 1/1,000,000th of atmospheric pressure. But there's another problem. At these minuscule levels, even quantum mechanics are a nuisance because they introduce randomness into photon behavior. LIGO mitigates this with an optical cavity which squeezes the light. This squeezing minimizes the light phase's noise and squeezes it into amplitude noise, which the interferometer doesn't measure.